Hello, and welcome to my video on derivatives in the shape of a graph. In this video, I will be mainly going over finding concavity and points of inflection, as well as doing a recap on critical numbers increasing or decreasing, and finding local maximum and minimum. First and foremost, let's go back to the definition of increasing and decreasing functions. Below is a definition of such. With this in mind, we can test for increasing and decreasing functions with the following statements. If this is still confusing to you, I have two example questions involving increasing and decreasing. For the first one, we find critical numbers by setting the derivative equal to 0, getting test values that fall correctly in line with its intervals, plugging those values into the derivative equation for either positive or negative values that show increasing or decreasing, respectively. My results show an increase, then a decrease, then an increase again, and the intervals of increasing are at x is less than -3 and x is greater than 1. Since this is just a review, I'll provide an image of the second question that you can pause to look at for more detail if you wish. Finding relative or local minimum and maximum requires the same steps as finding the intervals of increasing and decreasing in a function, only it goes a step further. Let's look at a new example. So here we found our critical numbers 0, -1, and +1 and plugged in test values as so. Remember that the negative and positive signs at the end indicate whether the graph is increasing or decreasing on a specific interval. In this case, the graph decreases from -infinity to 0, then increases from 0 to infinity. The change in sign value looks like a curve or a U on a graph and represents the local maximum or minimum of the graph. If the curve looks like a normal U, it's a local minimum. And if the curve looks like an upside down U, it's a local maximum. Because there's a sign change in when x equals 0, we can deduce that there's a local max or min at x equals 0. To determine which, let us draw a curve of the graph. Before x equals 0, the curve is decreasing, and at 0, the curve's path changes so that it's increasing. This looks like a U, so it's a relative minimum. Anyway, we plug x into the original equation, not the derivative, for a value of -1, which represents the y value. So the relative min occurs at 0, -1. Now that we touched up on the basics, let's dive into concavity and points of inflection. Concavity is, in my opinion, easiest to see with a graph. Don't look at the green tangent lines for now. Just look at the shape of the curve. With concave up, the curve looks like it's opening up. With concave down, the curve looks like it's opening down. Now let's look at the tangent lines. The tangent lines are below the curve when it's concave up. Just as the slope of the curve is increasing, so is the derivative. The second derivative, in addition, is positive. For concave down, which has a frown, the slope of the curve is decreasing, and so is its derivative. And the second derivative is going to be negative. One more time. For concave up, increasing slope of a curve, increasing derivative value, and positive second derivative. For concave down, decreasing slope of curve, decreasing derivative value, and negative second derivative. Since the second derivative will be positive for concave up and negative for concave down, we can agree with the following statement. If the second derivative is greater than 0 for all x in some interval I, then f of x is concave up on I. If the second derivative is less than 0 for all x in some interval I, then f of x is concave down on I. Now if the second derivative were equal to 0, then there would be no concavity. Notice that concavity and the increasing or decreasing aspect of the function is completely separate, and they do not have anything to do with each other. This is important to note because a common mistake is to mix these two up and use information about one to get information about the other. There's one more definition we need to cover before we go through what is called the second derivative test, and that is what an inflection point is. A point of inflection, or a POI, is a point on a graph where the concavity changes. In order to find one, we need to look for when the second derivative changes sign, much like how we look for a relative max or min by the change of sign in the first derivative. Here is an example sketch of a point of inflection on a graph's function. The concavity changes from concave down to concave up. Good news, guys. This is the last new concept I will go over. In addition to the first derivative test, we can use the second derivative test to find local minimum and maximum values. The second derivative test states that if the second derivative of f of c is less than 0, then there's a relative max at c, f of c. If it were greater than 0, then there's a relative min at c, f of c. And if it were equal to 0, then at where x equals c can be a relative max, relative min, or neither. Which of these three the graph has at x equals c is something we cannot find with the second derivative, so we must seek help by using the first derivative test instead. So, let's apply all this new knowledge to answering some practice problems now, shall we? 1. Determine the points of inflection and discuss the concavity. Before we dive into this problem, we need to ask ourselves, is the graph of this function continuous? We can plug this equation into a graphing calculator or just check ourselves and find that yes, it is. Next we find the derivative of this function, which is 4x cubed minus 3x squared, as well as the second derivative, 12x squared minus 6x. Cool. Since we're looking for points of inflection and concavity instead of critical numbers in relative maximum or minimum, we set the second derivative equal to 0. In doing so, we are finding the possible points of inflection, or where we predict concavity to change. After setting the second derivative equal to 0, we get x equals 0 and 1/2. It helps, like before, to put these values on a number line so that, in a sense, we can more easily find test values in between number values. For a number between negative infinity and 0, I used negative 1. For between 0 and 1/2, I used 0.1. And for 1/2 to infinity, I used 1. After plugging these test values into my second derivative, I got a positive number, a negative number, and a positive number again. You don't have to solve for the exact value, just know its sign value, since that's what determines concavity. Positive is concave up, negative is down, and positive is up again. If I were to draw a graph simply visualizing the order of concavity above, it might look something like this. Again, it could look different, so long as the graph goes concave up, down, and up again. Because the concavity changes at these x values, we can say that our possible points of inflection are indeed inflection points. We can then find the y value of the inflection point by plugging the x value into the original function's equation. With x equals 0, we get positive 1, and with x equals 1/2, we get positive 15 over 16. These would be our points of inflection, since the concavity is changing at these points, either from up or down, or vice versa. Now that we're used to finding concavity and points of inflection, here's a harder problem that I got from the UC Davis website. Keep in mind that with this function there's a domain restriction, meaning x goes only from negative 2 to positive 2, no further. We find the derivative using the product rule. This process turned out to be more grueling than those of the last examples. We set the derivative equal to 0 for critical numbers x equals 0, root 2, and negative root 2. I didn't have enough room to show the work, but you then plug in these green x values into the original function to get corresponding y values. These will be used to pinpoint maxima and minima, which will likely occur at positive and negative root 2 since the graph is undefined after positive and negative 2. The plugged-in test values, also not shown, gave me a decrease, then an increase, and another decrease. We then find the second derivative with the quotient rule and set it equal to 0 for possible points of inflection. We get 0 and positive and negative root 6. Now this is where knowing the domain restriction comes in handy. Positive and negative root 6 lie outside of the restriction, so we don't need to test these values as inflection points. We end up testing values between negative 2 and 0 and 2 by the values into the original equation as x's. We get a positive value for negative 2, 0, which represents concave up, and a negative value for 0, positive 2, which is concave down. If we plug 0 into the original equation, we can find the y value of the point of inflection, which is 0. Here is the overall answer for our work. Remember that I found the y value for the absolute max and min by plugging their respective x values into f of x. The graph would look like so. Thank you for watching.